The first light equation that is most fundamental is the relationship between the wavelength of light and the frequency of light, which is connected via a constant, the universal constant, or the universal speed limit, for the speed of light. C is the letter used for the speed of light in a vacuum. And that number is approximately 3.00 times 10 to the 8th meters per second. As you see for the units meters per second, the speed of light is the velocity of light. This upside down looking y is called a lambda, and that represents the wavelength of light. Wavelength is measured in meters. We're going to label the name of this upside down looking y because the Greek letter lambda is the real name for it. This looks like a script V, but this is called a nu, which is another Greek letter. You have to be careful not to use a V because some people will see the V and think it means velocity, but that is the reason why some people prefer to use F. I have gone back and forth between using F or nu to represent something that we call frequency. The frequency of a wave is measured in an inverse second because frequency is not a measure of how long it takes for something to happen. Frequency is a measure of how many times something can happen in 1 second. Frequency can be written as a 1 over an s, but collectively, an inverse second is called a hertz, which is abbreviated Hz, named after a scientist. Putting all the pieces together, we can see that the speed of light, c, is equal to the wavelength of light times the frequency. Notice how these two variables are next to each other. C is a constant, of course. The wavelength of light times the frequency of that light equals the speed of light, and all light, whether it is visible or not, travels at the speed of light. That includes radio waves, microwaves, red light, blue light, green light, and so on. Because C is a constant, you can look at these two variables on the right side, wavelength and frequency, and see that they are inversely proportional. That means that something with a high wavelength, or a long wavelength, has a low frequency. Something with a low wavelength, or a small wavelength, has a high frequency because those little waves will pass through a given point more times in a second than the longer waves. Here's what I mean in terms of color. Red light has a relatively long wavelength in the visible spectrum compared to blue light. Wavelength is the distance between one crest and the next crest, or one trough and the next trough. Crest to crest, this would be the wavelength, from one peak to the next. For blue light, you can see that the distance from one crest to the next crest is much smaller. Qualitatively, a high or a long wavelength corresponds to a low frequency, and a low or a small wavelength corresponds to a high frequency. And that is evident in the equation. There are types of light that have smaller wavelengths than blue light, such as ultraviolet or gamma, and their wavelengths are so small that their frequencies are relatively high, and they also have high energies, and that will be evident in the next equation. But before we get there, there's an important note about wavelength. Although wavelength has to be in meters when used in an equation, you will often see wavelength in nanometers, especially for visible light. So red light, for example, has a wavelength of approximately 700 nanometers. It's a range. 700 nanometers is a type of distance, so it does fit a descriptor for wavelength, but if we need to use that wavelength in an equation, we need to first convert to meters. 700 nanometers, I'm going to convert nanometers to meters with the understanding of this important concept. 1 meter actually contains 1 billion, or 1 times 10 to the ninth, nanometers, because 1 nanometer is a billionth of a meter. Nano, as a prefix, means billionth. Light waves are very small, so it's convenient sometimes to talk about them in higher integers such as 700 nanometers. But mathematically, 700 nanometers turned into meters is 7.00 sig figs, don't worry about the sig figs, times 10 to the negative 7th meters. So if someone gives you the wavelength of light, say 700 nanometers, and asks you to calculate the frequency of that light, before you put it into the equation that you just saw, you need to first convert it into meters, because that is what's standard. Now we're going to talk about how frequency is related to energy, because as you see in this equation, C equals lambda nu, this does not mention energy. Energy, measured often in joules, is proportional to the frequency of light. But there is a proportionality constant called Planck's constant that relates the two. Max Planck was a scientist who was a pioneer in much of the chemistry and physics. I think he was a physicist in light and energy. Planck's constant is represented by the letter H, and the units for Planck's constant is a joule second. Not a joule per second, but a joule second. Planck's constant numerically is 6.626 times 10 to the negative 34th joule seconds. Nu, or occasionally F, is of course still the frequency. And frequency is still measured in a unit called the hertz, which in standard units is represented by an s to the negative 1. Putting all the pieces together, the energy of a wave is equal to, or the energy of a photon, is equal to h, which is Planck's constant, times nu. Occasionally, like I said, you will see an F instead. But I'm going to get rid of the HF because I prefer to use nu now. If you check the units, you see that E, which is measured in joules, is equal to H, which is a proportionality constant of a joule second, times nu, which is an inverse second. What ends up happening is that the second cancels on the top and then the inverse on the bottom, giving you just joules. Importantly, notice how energy and frequency are on opposite sides of a constant, which is h. That indicates that frequency and energy are directly proportional, meaning that as the frequency of a wave increases, so does the energy that it carries. Let's take a look again at red light versus blue light. We know already the relationship between wavelength and frequency, but this equation proves the relationship between energy and frequency. Blue light has a smaller wavelength and a higher frequency. Because blue light has a high frequency, it also has a high energy. Red light has a low frequency and therefore a low energy relative to blue. Using some algebra skills, you can combine the first equation with the second equation to relate, say, wavelength with energy, using simple substitution. Here are our two equations. The first thing I'm going to do is rearrange the first equation to solve for nu by dividing both sides by lambda. C divided by lambda, or the speed of light divided by the wavelength, equals the frequency. I can now take this and substitute it into where frequency is in the energy frequency equation. Doing so gives me energy equals h, Planck's constant, times c over lambda. Now let's think about the relationship that this presents to us. We have the wavelength in the denominator relative to energy, which indicates that as wavelength increases, the energy decreases. And we know that already because an increase in wavelength leads to a decrease in frequency, and a decrease in frequency would lead to a decrease in energy according to the second equation. This equation may not be provided to you because you should know how to substitute one equation into another equation. When given this equation, remember that c and h are both constants. C, the speed of light, is 3 times 10 to the 8th meters per second. H, Planck's constant, is 6.626 times 10 to the negative 34th joule seconds. The units do cancel out. For our quick practice, we're not going to do any actual calculations. We're just going to think about the equations and their relative relationships. Consider these two waves. One wave has a wavelength of 650 nanometers, and the other one has a wavelength of 480 nanometers. Which one has a higher lambda, which we know is wavelength? Of course, the answer is the one with 650 nanometers. 650 nanometers, regardless of if you turn it into meters or not, is still a higher wavelength than 480 nanometers. 650 nanometers is 6.5 times 10 to the negative 7th meters, which has a lower frequency. If you think about our equation that relates wavelength and frequency, we know that c equals lambda nu. Because those two variables are next to each other, we know that they are inversely proportional. A higher wavelength indicates a lower frequency. So the answer is actually the same. The 650 nanometer wave has a higher wavelength and therefore a lower frequency. Which is faster? This is not necessarily a trick question, because you know that all wavelengths of light, regardless of their wavelengths or their frequency, all wavelengths and frequencies of light travel at the speed of light, so they are the same. They have the same velocity, which is the speed of light. Which has more energy? Now you have to think about the substituted equation. We know that c equals lambda nu, therefore nu equals c over lambda. Plugging c over lambda into the energy equation, which we know is E equals h nu, gives us the derived equation E equals h times c over lambda. Thinking about their positions, one with a higher wavelength will have a lower energy. So we're thinking about the one that has more energy, which means the answer is the one that has the smaller wavelength. Smaller wavelength, higher frequency, higher energy. And the answer to this question then is the 480 nanometer wave.